Welcome back. Gray Monday morning. So, QR factorization. I pretty much. Oh, you know what? I haven't quite finished looking at the code. Let's do that. I'm sorry. There's one more thing. A couple more things I want to talk about the code for QR before we go on to chapter 6. Oh, no, don't do that. Don't do that. Don't do that. There we go. Okay. So we left off looking at this QR factorization. And let's see. So how far did we get? It's been a long weekend. So we went through. Okay, so we're starting off the rows and columns, the columns of R and V. And so this is constructing the column pointer, so they're building it left to right. And the first thing that we have to do is we've got to do the e-reach, find the non-zero pattern of the kth row of L, or the kth column of R. And that's what this does. It just takes the tree and walks up the tree. The only twist is that this leftmost idea, it starts, for any given column, it starts with the column index of the leftmost entry in that row. And so then it pushes that path onto stack, because we need to do it in topological order, because we're doing numerical work, and the householders depend on each other, so they've got to be done in the right order. And then as we walk through this, and if we find any new row indices we haven't seen before, we have to add them to the non-zero pattern of V. So this right here is just adding on the non-zeros in the A matrix, not in the tree. Okay. Because the other householder vectors are going to come from the children. So that's what this does. We go through then each column of R. So each row index in the kth column of R. So it's going through each of these non-zero entries, applying their respective householders to this matrix. And at this point, then so here's the application of the householder. I'm not going to go into the details of how that's done. That's just that householder vector multiplication. Those entries are stuck onto the R matrix, because we haven't actually computed the pattern yet, but it's copied now. We have the pattern of the kth column here, but now it's assigned into the matrix R at this point. So, and then finally, I reuse this scatter function to do the set union. So I'm actually, this is a bit overkill. I could have done this a little bit more efficiently, but it just keeps the code short, because I know that these V vectors are going to be disjoint with each other. But they're not necessarily disjoint with all the non-zeros here. So I could have kept track of that queuing business before, that I used before in the symbolic analysis, to keep track of all of those unique entries in this column from the A matrix. And then each of these householder vectors are also unique, and I could just concatenate them together. But I decided that I would punt and just use gather scatter at this point to do the set union anyway, because then I can just use a very simple assignment here. I can allow for some overlap. So there's an entry here that I don't actually need, but I put it there just because it's simpler, and then I don't have to keep track of the queues all over again. I would have had done that all over again, and it would have made the code a lot longer. So then once the householder vector, once all the householder vectors are applied to this vector x, and the non-zero pattern has been computed, then we can gather those results back to the householder vector. It's not yet the householder vector, but it's the kth column of the updated matrix. It's gathered into the Vx vector, because that V vector is going to become, so that's what's being modified here. So I'm taking all these updates and modifying this piece of the matrix. See, these entries up here of this X vector have already been written into the R matrix. So there's a vector X that's doing all of this work. It's representing that entire column. The top half of it, above the diagonal, is the column of R. And the thing below the diagonal is the column of the householder vector, or the updated matrix. So finally, when that householder vector is constructed, when the kth updated column of the A matrix is constructed, then we can find the householder vector that annihilates it. So this has been modified, this has been computed and applied. All the householder vectors have been applied to this column. Now we need to find a householder vector that annihilates this column. And that's what this last step does right here. And it's the very last thing that's done, because it's a left-looking algorithm. That householder vector is not yet applied. It will be applied then later on to the right. And that's it. There's a lot of little minor details about how these functions work, computing the householder vector and applying it. I won't go into those details, because I really haven't shown you anyway the numerics behind this. I just stated it, and so rather than go into all the details, we don't really need to understand the details to understand how the structure of this algorithm works. So that's sparse QR. It's slightly more. It is more complicated than say Cholesky factorization, but it's still not too bad. I mean, it's 73 lines of code, gives you a decent QR factorization. Now, it's not quite as good as. I mean, there are other alternatives to this QR factorization, and I've got my slides ready to jump into LU factorization, but I think, let's see. So what I'll do is I'll come back. I think it'd be useful. I've got some slides I could show you on the sparse multifrontal QR, which is really interesting. And I did this since the book, and so didn't have the slides here yet together. So I'll do that next class. But the gist of that method is that it exploits this idea that the matrix is split into 4 pieces for every householder. You have a collection of entries here that you can annihilate, and this is all 0 down here. And then this is 0 as well. So this is a 0 section. This is a 0 part of the matrix, just by definition. These are all the non-zeros in the first column, and these are then 0. And these are all the columns that's the set union of these non-zero patterns of all these rows. So it's any non-zero here will be on this half, and then this will all be 0. And then this is just any arbitrary structure. And then what happens when the householder hits is that when you annihilate this, all of this becomes completely non-zero. Well, that's really powerful to exploit, because what happens if, say, the next column has the same set of rows? What if, for instance, this is also 0? Okay, then what you can do is you can say, well, no, I'm not going to work on a sparse matrix. I'm going to take this piece right here as a little dense matrix. And I'm going to take this piece of the matrix and I'm going to do a dense QR factorization to annihilate this to 0. And And the left-looking QR would stop at this point, but you can actually keep going because there's nothing. You've got a set of rows; they're independent from the other rows. You don't have to. I mean, even though there's non-zero values right down here, you can apply a partial householder operation to zero this out, to zero this piece of the matrix out, to get something like this. So you take a divot into the matrix, basically. And it turns out that this reduces the non-zeros in V quite a bit. Okay, because it's more aggressive in looking further to the right at each step. And the V matrix here will have more non-zeros in it than the collection of householders will for the multifrontal QR. So this is a more compact representation of the Q matrix. So this is what happens inside the MATLAB QR. So I will pull out my notes for that and show that to you next class. That was anyway. So that's the QR. Oh, come on. So, any questions about QR factorization, or should I dive into LU? So now we're at the last major direct sparse matrix method, and this is LU factorization. And this is really, in a sense, the grandfather of them all. It's really the first one that was tackled because well, QR is more general; it can handle any matrix, but it's almost too powerful. Okay, this is the basic workhorse of matrix computations is LU factorization. And in LU factorization, what you want to do is you take a matrix A and you factor it into a product of a lower triangular matrix and an upper triangular matrix. Okay. And but what can easily happen, which does not happen in Cholesky and it does not happen in QR factorization, is that this can fail for matrices that otherwise you would think have a nice LU factorization. This matrix here, for instance, is just a permuted upper or lower, depending on how you look at it. It's really just a permuted upper or lower triangular matrix. But if you try to do the first step of Gaussian elimination on this matrix, you take what you do to find LU, do an LU factorization. It's an elimination process, and one way of looking at it is you take the first equation, you solve for the first unknown, and you eliminate that unknown from the other equations. Well, the first unknown does not appear in the first equation, so you have to divide by 0 and it fails. You can't do it. So there's lots of strategies to avoid this problem. The basic one, the simplest one, is called partial pivoting. The idea is, okay, you're at the first column, and you say, well, wait a minute. I don't want to necessarily pick this entry and this equation. I'm going to pick this unknown to remove from the other equations. But then which equation will I use to do that? Well, let's use this one instead. And so let's swap these two. So now we have this matrix, and now the LU factorization is easy. It's just L is identity and U is upper triangular. And what happens is then the factorization looks like this. It's a permutation, a row permutation P times A equals L times U. And then this thing can be used to solve a linear system, among other things. And so just to show you how that works, if I have AX equals B and I'm trying to find X, I can multiply both sides by P to get this equation. And P is an orthogonal matrix. It's a permutation, so that just rearranges the rows. It rearranges your equations. It doesn't do anything to your solution. And then PA equals, if I do LU factorization of P times A, I have LUX equals P times B. And now I can solve this with the following. I can let y equals u times x, which I don't know how to solve yet. But now I have Ly equals PB. And that's a sparse, that's a lower triangular system. I can solve this for y and then plug it in here and solve ux equals y for x, and we're done. So LU factorization with partial pivoting, followed by a permutation on the right-hand side, followed by a forward solve, followed by a backward solve, and you've got your solution. So it's a very straightforward process, but there's one problem with this that we haven't tackled yet, and that's Chapter 7, is the field-reducing ordering. That's this NP-hard problem that says, wait a minute, what if this gives me too many non-zeros in L and U? Okay, that's a serious combinatorial problem that we'll address later. Okay, how do we fix this so that it actually can work? Okay, because this can really cause horrific problems. I mean, just to give a look ahead to Chapter 7. I think maybe I've shown you this diagram before. Suppose this is your matrix. Okay, and suppose partial pivoting decides to pick this entry on the diagonal. So you have a system of equations. This equation right here involves every unknown. And these other equations just involve two of them. Now, it would be really stupid to say, I don't mean to say you are, that was a slip of the tongue there. It would be really a bad idea to take this first equation, solve for x1, the first unknown, and plug it into this equation to remove this x1 from the equation that says x1 plus x2 equals 42. I mean, that would be ridiculous. Because then this equation would have all the unknowns. And so would this one. And so would this one. And what you've done then, you've replaced a sparse matrix with a dense one. So forget it. Throw away sparsity. This is, of course, an extreme case. So what you want to do instead is, well, don't use this equation and don't use this unknown first. You can solve for the unknowns in any order. I could pick this equation and I could pick, say, this unknown and remove this unknown from all the other equations. There's nothing, I mean, I could pick any non-zero here and permute it to the diagonal, in other words. So the question then becomes for Chapter 7, just as looking ahead, how do you find the optimal ordering that reduces the number of non-zeros in L and U? And that's the NP-hard problem, which cannot be solved. So Chapter 7 is trying to solve an unsolvable problem. But we're not there yet. So let's do Chapter 6. But that's just a look ahead. So we're going to have to rearrange this and do some permutations. And you'll see that filter into Chapter 6. You'll see places where, oh, well, wait, what if we're factoring a permuted matrix? And, well, that's to reduce fill-in, but we'll do that later. So that's why I'm kind of giving, again, a reminder of look ahead to Chapter 7, that we're going to have to worry about permutations to reduce fill-in. So now, with what's interesting about LU factorization, and it's sort of like a game in a theoretical sense. It is a game in a theoretical sense. That there's a competition between two kinds of permutations. There's one kind of permutation that says, I want to reduce fill-in. And there's another kind of permutation that says, oh, wait, you want large entries on the diagonal for numerical stability. And they fight with each other. There's the ordering that would give you the optimal fill-in would not be the ordering that would give you the optimal numerical accuracy, and vice versa. They're different. And so there's a trade-off between them. You've got to constrain the symbolic ordering to say, look, I can only go so far. I can relax the numerical pivoting a little bit to give the symbolic pivoting freedom to reduce fill-in. this kind of trade-off, this back and forth between ordering for accuracy and ordering for fill-in doesn't occur in Cholesky factorization or QR. Because in Cholesky factorization, any permutation of the diagonal works great. There's no numerical constraints. We didn't talk about any numerical issues there because there are none. It's just any permutation. If the matrix is symmetric and positive definite and at all well-conditioned or not horribly ill-conditioned, then any diagonal permutation works. If it's extremely ill-conditioned, you don't want to use Cholesky factorization anyway. So Cholesky doesn't care what the numerics are. So there's no feedback between the numerical factorization and the symbolic. It's just do the symbolic, that's it, you know the pattern, you're done, and then do the numeric. Same thing with QR. With QR, when we applied this householder vector, all I cared with it was that symbolically that this is an entry in the matrix, the diagonal. And the only reason I cared about that was to make my theories work a little nicer that says that the householder vector and this column of the A matrix has the same non-zero pattern. If it doesn't, if there's an entry there that's missing, then the householder vector has one extra entry, and that's awkward. So just permute this and call that, take any one of these entries and permute it up to the top. Well, at this point, the orthogonal rotations are very stable numerically. Because what's happening here is you've got this vector, okay? And imagine you have a vector that has, say, no x-coordinate at all. It's only in the yz plane like this. So the x would go out this way. Maybe the x-coordinate is just very, very tiny, okay? It doesn't matter, because what's going to happen with QR factorization, we're going to take this column, this first vector, and rotate it so that it lies along the x-axis. So this very, very small value in the x-coordinate doesn't matter. I'm going to take this column and just take this vector and just splat it rotate it until it lines up along the x-axis. And that rotation doesn't change the length of this vector. And so it doesn't make, see, the thing with numerical concerns is you don't want to take very, very tiny entries and make them very big. Because if you have a very, very tiny entry and a very, very big entry, and you just arbitrarily make this small entry very large and add it to the big entry, just scale and divide and such, then a small amount of noise in that small value can make a huge change in the larger value, and it can throw away data that you had in the bigger number. It can throw away significant bits, and that's bad. But with householder, that's not a concern with orthogonal operations, because the total size of the problem, the length of this column, does not get any bigger. We don't have small values getting big. You have the x-coordinate getting from very small to very large, but the problem itself, the vector itself, does not grow in size. The norm of this vector doesn't change. So essentially what's happening with this householder operation, it's sort of like a permutation. A permutation is also an orthogonal operation. And a permutation that makes this 0 equal to 1 is very safe. You just swap. There's no loss of information at all. So orthogonal operations are perfectly safe numerically. Even if that first entry, the pivot, is 0, it's very safe. So there's no concerns with numerical considerations with QR, no concerns with Cholesky. Unless you've got an ill-conditioned matrix or rank-deficient matrix, then there are issues with QR. You've got to be careful about how you handle rank-deficient matrices. Okay, systems of equations that don't have a solution. They're underdetermined. That's a different problem. If it's at all well-defined in terms of rank, if it's full rank, then QR doesn't care, and Cholesky doesn't care. But LU cares. We have to worry about this value here, and we want to put a value there that's big enough. So LU factorization. Let's look at how this works, and I'll derive this from scratch, just like the other methods. First, let's see. Let me look first at some structural issues. And this is the connection between LU and QR. So Cholesky forms a basis for QR. And the theory we use for QR forms the theory we use for LU. So this is the flow of the conceptual thought from Cholesky to QR to LU factorization. And the connection between QR and LU is the following. Basically, R, the non-zero pattern of R, is a superset of the non-zero pattern of U. And Q, or I should really say V, the collection of householder vectors, is a superset of L. That's what these two theorems say here on the board, that they're in the book. Basically, R is an upper bound on U. Uij can be non-zero if and only if Rij is non-zero. And assuming a zero-free diagonal, the householder matrix is an upper bound on the non-zero pattern of L, whatever L you obtain with partial pivoting. So here's the reason that happens. And I could use, let's see, I'll just redraw it. So remember with QR factorization, let's just write the first. So I'll just illustrate this rather than going through a formal proof. I think it's more useful. Okay, so suppose you pretend that we've rearranged the matrix. Of course, this is just for pretend. Such that the first column here has all the non-zeros in that column that appear first and then 0 down below it. Okay, it's just a view of the matrix. I mean, this might be row 2 and this might be row 47 and 33. It doesn't matter, okay, what exactly these rows are. Let's just rearrange the matrix so it's easy to look at. And then these are all 0. And then a column is here if any entry is non-zero in that column, in that first set of rows. Okay, this is what we looked at for QR, this structure. So now, let's put some values here, or some pattern. Okay, suppose and this we don't care about. This we don't care about. So what happens with QR factorization? QR factorization is going to do a householder operation to annihilate all but the first entry. It's going to annihilate this column. And in the process, it's going to take all of these rows and replace all the rows with a set union of all of them. So it all becomes non-zero. All those entries become non-zero. And then the first column of the householder vector is this pattern here, and the row of R is this non-zero pattern. The row of R is the set union of all possible rows, of all those rows that took part in the computation. So that's QR. Well, with LU factorization, what happens is a little different. And I could derive this. I don't have it on the board, but I could derive it if you like. We have just plain old Gaussian elimination outer product. Why don't I derive this first, and then I could be more rigorous. So what I'm going to do, L11, and I'm going to call this 1 by 1. So this is L21, L22. So I'm taking LU equals A, and let's for the moment forget pivoting. Okay, just adds complexity to the equations, and you can throw it away without loss of generality. In other words, forget it, and we can pretend that the matrix is already permuted. So we can pretend that that's the column we're going to choose for the moment. Now this outer product algorithm is not the one I'm going to show you for the sparse case. Okay, it's just going to be used to understand what's going to happen to the pattern over here. And so let me make some other let me write some equations down. So we have L11, U11, which are scalars, equals A11. So this is a scalar, this is a row vector, that's a column vector, and that's a matrix. So we've got L11, U11 equals A11. And then I have, let's see, I have L11, U12 equals A12. I've got L21, U11 equals A21. And then we've got L21, U12 plus L22, U22 equals A22. So those are the four equations that pop out of this block matrix multiply. Okay. And if you look at this carefully, you realize we've got too many unknowns, if you will, for too few equations. Let's assume by induction, well, no, by induction I'm going to solve this problem. I'm going to operate on this in a right-looking fashion. So I want to compute. I want to compute what L11 is, what U11 is, and so forth. I want to compute these entries and those entries. So at the kth step, I want to compute the leading row of U and the leading column of L. So I don't know anything, in other words. I haven't computed anything yet. And then the inductive part is going to be an LU factorization of the remaining submatrix. But the problem here is that I have essentially 6 quantities which I don't know. These 3 here and those 3 there. And I've only got 4 equations. So I have some freedom in how I choose to make this LU factorization work. In fact, many choices will work. And one choice I'll just arbitrarily make, and this is pretty common, is just force L11 to be 1. So I'll put a 1 here. And now the rest of it will all fall apart. Okay. If L11 is 1, so this drops out. And now I immediately have U11 and U12. We're done. Okay. And now that I have U11, I have A21, I can solve for L21. So here I can do L21 equals A21 divided by the scalar U11. So that's equivalent to dividing by the pivot. Dividing that first column by the pivot. And then I can take this equation, which now has 2 things that I don't know. I know now L21 and U12. I've solved for them here and here. I don't know these 2 terms, L22 and U22, but I can compute them inductively. I can say that L22, U22 is equal to A22 minus, and this is the outer product, L21, U12. And then you would just repeat this inductively. So if I can compute this first step, then to do the LU factorization of n minus 1 to do the LU factorization of an n by n matrix, I have to, of course, do the base case, so 1 by 1. That's easy. That's just L11 equals 1 and U11 equals A1. So we're done for a 1 by 1 matrix. So to do the LU factorization of an n by n matrix, I can make this modification here. I can find U11, U12, L11, and L21 here with these 4 equations. And then I can solve a problem of size n minus 1. So if by induction I can solve, if I can do an n minus 1 by n minus 1 LU factorization, then I can do an n by n. So it's an inductive algorithm. And of course, the recursion then just unrolls and it becomes a loop. So this is outer product LU factorization. And in the important thing to observe is at the kth step of factorization, then what happens is, we're ignoring pivoting. We have this vector u. This is u1, 2. And we have this column which I called L21. And what happens is that L21 is multiplied by U12 and then added to A22. And then we repeat. So the non-zero product, the non-zero pattern of an outer product is very simple. It just looks like this. And this is then added. This structure here is added, well, subtracted, okay? But symbolically, it doesn't. I'm adding entries to the A22 matrix. So this corresponds to conventional Gaussian elimination, where you take this pivot row, you solve for this equation, and you then add this equation to this equation, to this one, to this one, to this one, in order to zero out all these terms. And in doing so, these, and I've written them as 12, these 12 entries in the remaining matrix become non-zero. So if they were zero before, they'll be non-zero now. If they're non-zero before, they'll stay non-zero because we're ignoring numerical cancellation. So what does this have to do with QR factorization? Well, now let's look over here. Think of what would have happened if I wasn't doing QR, if instead I was doing LU factorization. If this was the first pivot row, then not all this becomes non-zero. But some of it does. This one, and this one. But you see, I haven't written outside the box, have I? I haven't put any entries here. I haven't put any new entries here. And there's no new non-zeros that appear here. They only appeared inside this box. So QR factorization fills up the whole box. LU factorization can only add to the box. It may not make it completely non-zero. So you see, LU is bounded below, in terms of the non-zero pattern, by the QR. Nothing the LU can do can exceed what could have been done by QR, because QR would make the whole box non-zero. This also extends, and this is really cool, it also extends to arbitrary partial pivoting. Now let's consider partial pivoting. With partial pivoting, and I won't go through it with this block 2x2 derivation because it's too complicated. It can be done, but it doesn't really give you much insight, I think. I've tried it. It's kind of ugly. But with partial pivoting, what happens is you decide, oh, wait, this value is too small. I'm going to pick this number instead, and I'll swap it to the top. So I'll permute this, and then I will do the outer product. Okay, but of course it might be a different non-zero pattern altogether than this pivot row. So I might have instead, for instance, over here, now consider this structure. What is this? These are all 0. So they are not candidates for partial pivoting. They're too small. They're 0. I want to pick the biggest number in this column with partial pivoting and permute it to the diagonal. That gives me good numerics. If I pick the biggest numerical value and swap it here. Now, symbolically, before I start, I don't know which is the non-zero, which is the biggest non-zero, because that's a numerical consideration. So really, structurally speaking, any one of these could be chosen as a pivot. But no matter which one you choose as a pivot, pick this one and swap it here, and then use it to annihilate those 4 entries. What will happen is these will become non-zero, right? If this is the pivot, if you choose this as the pivot row, those 5 entries become non-zero. Well, that might not happen. Maybe I'll choose this one instead. Well, if I choose this one, then these 2 columns fill in. Just like this over here. Okay, any entry in the pivot causes fill-in in the column below it, but only in those rows for which there's a non-zero in the pivot column. But this is the entire pivot column right here. So this column and this column become non-zero. Or, and I know I've wiped out my x's. Oh well. But in any case, if I pick this one, again, only say this column, and now I've completely obliterated my problem. If I pick this pivot row, maybe only those 3 columns become non-zero. Every one of those choices, which I don't know ahead of time which choice I'll make, because I don't know the numerical values ahead of time, symbolically. But no matter which choice I make, no matter which of these entries are biggest, I know that these are structurally non-zero. That is to say, there's no way these will become a pivot choice, because they're hard zeros. They're not in the data structure. They don't appear. They will not magically become non-zero. Only these will be candidates. But QR factorization then is an upper bound. Basically what QR factorization is saying versus LU factorization. LU factorization is like this. It's saying, well, you've got a bunch of candidate pivot rows. Pick one, any one. Pick one of these 5, swap it here, and then do the fill-in. Okay, so which pivot row will you pick? Well, I don't know. What QR factorization does, instead, it says, well, here's your 5 pivot choices. Pick all of them. Right? Because your pivot row, your row of R, is the set union of all of your candidate pivot choices for LU factorization or partial pivoting. So QR factorization is rather like, symbolically, like saying, well, we're doing LU factorization, and you're going to pick a pivot row from the first column. And the non-zero pattern of that pivot row is the set union of all the candidates. So it's an upper bound. So no matter which one you pick, it's going to be in that set union. So that's the relationship between QR and LU, and this is why we have the 2 theorems here. That R is an upper bound on U, because R for QR says, well, all of these will be there. LU will say, well, no, not necessarily. Maybe just this one, and maybe those 4 instead of all 6 or whatever. You see, it's an upper bound. The QR is an upper bound on any partial pivoting choice. That's what's really cool, is that the upper bound applies regardless of what the numerical values are. The only assumption I've made is that this entry is non-zero. The diagonal is non-zero. And that's what the assumption here is. So this is the relationship between LU and QR. QR provides an upper bound on fill-in. And so if we want to get an estimate, a worst case estimate of the fill-in in LU, well, we have it already then. We know how to do a symbolic Cholesky factorization. We can do a Cholesky factorization of A transpose A. That tells us precisely what Q and R look like. And Q and R gives us a bound on L and U. And a bound is good. If I know that, look, L and U can be no bigger than this, then that gives me a worst case scenario as to how bad the problem can be to solve. Now, the thing of it is, though, is that that bound can be rather loose. So you don't want to always just force that bound and say, well, this is LU and we're done. We're going to say allocate space for the bound and then do LU factorization in that space, because the bound might be way too large. But it is still a useful bound. The other thing that this gives us is for Chapter 7, it's going to give us a useful way of doing fill-reducing ordering. Okay, because if we figure out how to do a fill-reducing ordering on Cholesky of a matrix A, well then certainly I could form the matrix A transpose A and do a symmetric fill-reducing ordering on A transpose A. But see, this bounds the structure for R. This determines the structure of R. The Cholesky of A transpose A determines the structure of R. So if I can permute this matrix to reduce the fill-in Cholesky factorization of a matrix, then I can reduce the R for QR. And if I can reduce the fill-in R for QR, then I can reduce the bound on the U for LU. So all of these problems are related. So the fill-reducing ordering for one can be used for the other. The fill-reducing ordering of A transpose A for the symmetric problem can be used to reduce the bound on LU, and that gives a column permutation. And that's a way of saying, well, I'm not going to eliminate these unknowns in this order. I'll change the column ordering around. And that's what the QR will say. If I have A transpose A, and if I permute the columns, it looks like this. Q is an unfortunate choice. It's not the Q for QR. Maybe I should call it P sub C. If I have a row permutation, it just cancels out. It doesn't change the pattern of R. So the row permutation can be left free for numerical partial pivoting. So I can rearrange the columns to reduce the non-zero pattern of R, and that then gives me a reduction on the bound for U, so column ordering here will reduce fill-in, and that leaves the row ordering free to pick the partial pivoting choice. So that's how all these problems are related, and we'll look more closely at how to do that fill-reducing ordering in Chapter 7. But so back to LU factorization. LU factorization, though, this bound I've just demonstrated with outer product over here. But outer product factorization is very difficult to do. It's very fast if you can do it right. Okay, but think about how you would implement this in a sparse matrix data structure. You have to take a matrix here and add to it a bunch of entries in the middle. That's ugly. Think about how you would write the code to do this. Take a matrix and then arbitrarily splat a bunch of non-zeros that may not have been there before right in the middle of the matrix. Ooh, that's not easy to do. Okay. People have done it. It's very hard. And it's very hard to get going, to make it go fast. So an outer product, this is called a right-looking method, because when you're at this step of the factorization and you look right, you do work to the right of you, is hard to do. And so for the book, and also often in practice, a left-looking method is used. And that's this picture here that I've got. And I don't have much time to derive this equation, but the idea here, I'll use the projector. With left-looking LU, the picture is a little bit different. So instead of that little 2x2 block, I've broken it up into 3x3 block matrix multiply. And I've broken it up so that this is a single column, and this is a single row. So call this the kth column and the kth row. So this L11 matrix is k minus 1 by k minus 1. So this right here looks just like, in fact, the up-looking Cholesky. Remember that. This is the chunk of the matrix, and this is the last piece. Well, now I've got a little bit more of it. So I'm slicing it in the middle. So the same thing with the U matrix. This is k minus 1 by k minus 1. This is a scalar, and this is n minus k by n minus k. This is the rest of the matrix. And the same thing here. This is cut in the same way, rows and columns. This is k minus 1, this is 1, this is n minus size n minus k by n minus k. Now let's suppose by induction that my inductive hypothesis will be I know what these first k minus 1 columns are of L. So let's suppose I know these three terms. And I know this term. I know the first k minus 1 columns of U. So that's the inductive hypothesis. And of course I know all of A. Now the question is if I know the first k minus 1 columns, can I compute the kth column of both L and U? If I know the first k minus 1 columns, can I compute the kth column? The answer is yes, otherwise I wouldn't be showing it to you. I would put it up here as, well, the answer is no, we can't find it. No, I wouldn't do that, right? Obviously, I'd show you something that, well, maybe I would, I don't know. And the answer is yes. What we can do is we can write down, there's 3 equations here. There's 9 equations total, but we only have to write down 3 of them. For these pieces here, there's the 3 equations for A12, A22, and A32 are these 3, and together we can solve them, and it turns out, surprise, surprise, to solve it we need a sparse lower triangular solve, which we have seen before. That's our Oliver twist coming back. So I'll pick up here then to show you how that sparse triangular solve works on Wednesday. Thank you.